Yes. Go away. Oh my God. All these things to close. There we go. All right, let's go ahead and get started. So we're starting off with some more implicit differentiation. Again, these are equations where you have usually x and y mixed up together, and you typically can't solve for y. This one you might be able to solve for y, but it would be terrible to do. And that's not the point. The point is to pretend like y is a function of x, differentiate both sides using the chain rule, knowing that y cubed is just some stuff cubed. So when we differentiate both sides, we're going to get the derivative of x to the fourth, which is 4x cubed. The derivative of some stuff to the third, which is 3 times our stuff to the second, times the derivative of our stuff. On the others, yes. Oh, thank you. Yeah, good call. Good call. Yep. And then on the other side, the derivative of sine of x is cosine of x, and the derivative of y is the derivative of y, dy dx. Or you can think of it as 1 times dy dx if you want to do it that way. It's also perfectly fine to write y prime instead of dy dx, which is usually what I actually prefer to write because it's less writing, but either way is fine. After this first step where we differentiate both sides, all the work after that is algebraic, meaning there is no more calculus to do. We're just now trying to solve an equation. Specifically, we're trying to isolate dy dx. The steps involved are usually bringing all the dy dx's to one side, factoring them out, and then dividing by the leftovers. So it doesn't really matter which side. I'm going to bring my dy dx's to the left. So I'm going to have 3y squared times dy dx minus dy dx coming over from the right-hand side. On the other side, I'll have cosine of x, and I'll subtract 4x cubed from both sides to get minus 4x cubed on the right. I kind of feel like we do these next two steps in one, but I'm going to do them in two. So I think we could skip this next step of writing dy dx factored out, leaving a 3y squared minus 1 behind, still equal to the same stuff on the right-hand side, and then dividing both sides by the 3y squared minus 1. So here we get dy dx equal to cosine of x minus 4x cubed divided by 3y squared minus 1. This is a pretty standard procedure for finding a derivative implicitly. That said, there's a couple twists we like to throw in. So here's one twist or change up. Yeah, let's do that one. So let's say we want to find the slope of the line tangent to the equation. Where'd you go? X squared plus x times y plus y squared equal to, sorry, I had a number here and it's wrong. 1 sec. 1 plus 2 plus 4 is 7. At the point 1, 2. So we're going to start off the same way. We're going to differentiate both sides. Again, because we can't really solve for y here. So the clue that we're doing implicit is often that you've got a bunch of x's and y's on both sides or mixed up on one side of this equation. So differentiating both sides, the derivative of x squared is 2x. The derivative of x times y, we're going to have to use the product rule. So the derivative of x is 1, leave the other thing alone, times y. Plus, then we switch, we leave the x alone, we multiply by the derivative of y, which is y prime, or dy dx if you prefer. Either way is fine. Plus, the derivative of some stuff squared is 2 times our stuff to the first power times the derivative of our stuff, or 2 times y prime. Finally, the derivative of 7 is 0. From this step, there's actually 2 different ways you can go if the question is to specifically find the slope of the tangent line or find the equation of the tangent line. You could do all the work we did before, which is actually not the best way to do it, but I'll still show it to you. You could then solve for y prime like we've done a couple times. We do it that way first. We're going to see, let's see, I've got my y prime term here and here, so I'm going to keep those on that side. So I've got x times y prime plus 2y times y prime. And on the other side, I'm going to have a minus 2x minus y. I'm then going to factor out the y prime, just like we do every time. So I'm going to have a y prime times x plus 2y equal to negative 2x minus y. And finally, we're going to get y prime equal to negative 2x minus y over x plus 2y. And then we can plug in the point and say that the derivative of y prime evaluated at the point 1, 2, we're just going to plug in 1 for each x and 2 for each y. So it's negative 2 times 1 minus 2 over 1 plus 2 times 2, which is going to be negative 4 over 5. And that wasn't too terrible, but there's a better way to go. So if we know we're trying to find the slope of the tangent line at a particular point, the first thing you can do after taking the derivative of both sides is plug in your point. You can plug in right away. So we're going to plug in the point 1, 2, and let's see what we got. We've got 2 times 1 plus 1 times 2 plus x times y prime. Well, x is 1, so that's 1 times y prime plus 2 times y prime. Let's 2 times 2 times y prime equal to 0. And then I think the arithmetic is a lot easier here. 2 plus 2 is 4. 1y prime plus 4y prime is 5y prime equal to 0 still. We need to keep the equality equal to 0. Subtract 4. Divide by 5. So y prime equal to negative 4/5. You get the same answer either way, but I think one way is a lot easier to do it than the other way. So if you're finding a derivative implicitly at a particular point, it's almost always the best way to do it is to take the derivative of both sides. You always have to start with that. But then instead of solving for y prime, plug in your point first and then solve for y prime. It's almost always going to be easier. Let's do 1 or 2 more examples of this process. Sure, let's look at this one, which is a little bit gnarlier. Let's say we want to, you think of number things. That was number 2. find the equation of the line tangent to, what have we got here? X squared plus y squared squared equal to x minus y squared at the point 1, -1. You should never check this, but this point should actually satisfy this equation. That's why I was having to do some mental math for the previous problem because I had the wrong value. But like, if someone gives you an equation like this, it doesn't help you at all to know whether or not this point is actually on the curve. They mean for it to be, even if it accidentally isn't. This one is, plug in 1 for x and -1 for y, you get 1 plus 1 squared, which is 2 squared, which is 4. And over here you get 1 minus minus 1, which is 2 squared, which is 4. So that point is on the curve, but sometimes people write these problems and accidentally make a mistake. And if it's on an exam, you shouldn't check. You should be like, yeah, that point's on the curve. I'm gonna take the derivative, plug it in, things will be fine. That's my advice anyways. Don't check to the curve unless you're asked. But we're not worried about that here. We're going to find the equation of the tangent line. So in addition to finding the slope, we then have to write the equation of the line with that slope through that point. So first we're going to find the slope by, of course, differentiating both sides of our equation. That is always, always, always the first step if we see an implicitly defined equation like this. All right, on the left side, okay, I've got some stuff squared, so my derivative is going to be 2 times that stuff to the first power times the derivative of the inside, which is going to be the derivative of x squared is 2x. The derivative of y squared is, well, y is, again, a function of x. So it's going to be 2 times y to the first times y prime. Equal to, on the right-hand side, the derivative of some stuff squared is 2 times our stuff to the first power. Again, you don't really have to write that first power. Times the derivative of the inside stuff here is 1 for the derivative of x minus y prime for the derivative of y. And really, this one is an excellent example of how terrible it would be to actually solve for y prime first. To solve for y prime, you'd have to FOIL this left side out and then FOIL this right side out and then grip. It's awful, 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 awful. We don't want to do that if we don't have to do that. We don't have to do that. We're going to plug in x equal to 1 and y equal to -1. So let's see what we get. So plugging in. So I'm not going to write 1 squared plus -1 squared. I'm going to do some simplifying along the way. So plugging in 1 for x, I get 2 times 1 squared is 1 plus -1 squared is also 1 times 2 times 1 is 2 plus 2 times -1 is -2 times y prime equal to 2 times 1 minus -1 times 1 minus y prime. This one's still kind of gross. And it's better than it would have been. So let's do some more simplifying. So here I've got 2 times 2, which is 4. So I've got 4 times. Now this part here, the only simplification I can do is write it as 2 minus 2 times y prime. On the right-hand side, 2 times 2 is 4 times 1 minus y prime. And instead of distributing the 4 on each side, although we could do it that way, we could also divide both sides by 4. Equally good. So divide both sides by 4. You get 2 minus 2y prime equals 1 minus y prime. Add 2y prime to the right-hand side. So I'm going to get a positive y prime on the right-hand side. Subtract 1 from the left-hand side. 2 minus 1 is 1. Or if you don't love dividing both sides by 4, you could multiply it out and say 8 minus 8y prime equals 4 minus 4y prime. And then add 8y prime to get 4y prime on the right. And subtract 4 to get 4 on the left. And then divide both sides by 4 and get y prime equal to 1. So what does that mean for us? It means that the slope of the tangent line to that equation at that point is positive 1. So we have everything we need to write the equation of the tangent line. We have the slope. Our slope is 1. We have the point. Our point is 1, -1. And then if you're James, which I am, you then use the point slope form and say y minus the y coordinate equals the slope times x minus the x coordinate. That is where I prefer to start if I'm writing the equation of the line. And then I would solve for y and say y plus 1 equals x minus 1. Subtract 1 from both sides, and you get y equal to x minus 2. That's the equation of my tangent line. That's pretty much all there is to say about implicit differentiation. If you're finding the derivative in general, take the derivative of both sides, do all the algebra to solve for y prime. If you're finding the slope of the tangent line or the slope at a particular point, take the derivative of both sides, plug in your point, then solve for y prime. One more thing I want to say, and then we'll move on to some related rates.
Sorry, could you just repeat the last, where the end starts?
Say that one more time. Right here.
Keep that bit. Yeah.
So I'm using the point slope formula here, which is the general point slope formula that's saying that if you have a point that the line goes through, x1 comma y1, and the slope, which we usually call m, then your equation is going to be y minus the y coordinate equal to your slope times x minus the x coordinate. So in this particular example, thank you, I did y minus the y coordinate of my point, which was -1, equal to my slope, which was 1, times x minus the x coordinate, which was +1. And then I simplified after that. So I said y minus -1 is y plus 1. I distributed the 1, or just said 1 times anything is just the thing. And then I subtracted 1 from both sides to get y equal to x minus 2. Or you could do y equals mx plus b, plug in your slope, plug in your point, solve for b. That's also totally good. It's just not the way I like to do it. There's one other thing I want to say. Oh, yeah. So, yeah, let me show you one more thing, because occasionally this comes up and it is worth knowing this. Let's say we were asked to find, well, didn't want to do that. Find dy dx given x equal to y squared plus 3x over x squared minus 5y cubed. And this looks awful, because it is. We could start taking the derivative right away implicitly. And on the right-hand side, it's going to be awful, because you're going to have to use the quotient rule, and you're going to have y primes up in it, like all in the numerator. There is a, what's the right word here? There's a way to get around that. You can manipulate this equation before you differentiate both sides. Specifically, you can get rid of the denominator by multiplying both sides by that denominator. So I would first say, okay, great. I'm going to have x times x squared minus 5y cubed equal to y squared plus 3x over x squared minus 5y cubed times x squared minus 5y cubed. On the right-hand side, the x squared minus 5y cubes divide out to 1. On the left-hand side, I'm going to distribute the x and get x cubed minus 5xy cubed equal to y squared plus 3x. And now it's going to be much less terrible to take the derivative of both sides and find y prime. So let's do that. So the derivative of x cubed is 3x squared minus, for our 5x times y cubed, I'm going to think of the product rule as a 5x times a y cubed. So when I take the derivative of the first thing, the derivative of 5x is 5. Leave the y cubed alone. Plus, now I'm going to leave the 5x alone. And the derivative of y cubed, or some stuff cubed, is 3 times y squared times the derivative of y. And I do have a minus sign in front of all that because it's minus the derivative of this product. So this minus sign will distribute to each of those two terms. On the right-hand side, the derivative of y squared is 2 times y times the derivative of y, plus the derivative of 3x is 3. And now we do the same sort of thing. I guess I have to distribute before I can start bringing all my dy dx's to the same side. So I have 3x squared minus 5y cubed minus, I would simplify this as 5 times 3, which is 15x y squared dy dx equal to 2y dy dx plus 3. Let's bring my dy dx's to the right-hand side just to change it up for once. So on the left, all the not dy dx terms will be 3x squared minus 5y cubed, and I'll bring the 3 over to the left-hand side as minus 3. On the right-hand side, I'll have my 2y times dy dx plus 15xy squared dy dx. I think in this step, you could also see how it's going to factor out and just kind of skip this and write it as dy dx times 2y plus 15xy squared, but you don't have to skip that step if you don't want to. So then a couple more steps here. Same thing on the left. On the right-hand side, I have 2y plus 15xy squared, all times the factored out dy dx. And then finally, dividing both sides by that, I'm going to get 3x squared minus 5y cubed minus 3 over 2y plus 15xy squared equal to my derivative. Something worth noting here. If you had decided to bring your dy dx's to the left and the other stuff to the right, your answer would still be correct, but it would look slightly different. So if you went the other way, your answer would look like negative 3x squared plus 5y cubed plus 3 divided by negative 2y minus 15xy squared. Essentially, everything in the numerator and the denominator changes signs. But it's still the same answer, because in this answer, you could factor out a -1 from the top and the bottom. Those would cancel, and then they would look exactly like that. Or you can multiply this by -1 over -1 and look exactly like that. And multiplying by -1 over -1 doesn't change your answer, because you're just multiplying by 1. So don't worry if your answer looks a little bit different than someone else's when you do this, because maybe you brought your dy dx's to the left and they brought their dy dx's to the right. Happens all the time. All right. So let's continue on here and talk about some related rates. And we'll start off with a pretty typical example. Yeah. So let's see. The radius of a circle is increasing at a constant rate of 2 inches per second. At the moment, the radius of the circle is 5 inches. How fast is the area changing? Actually, I'm going to write 2 questions here. Part A, how fast is the area changing? That's what we're asking. So here's what I would suggest. When you have a related rates problem, not always, but almost always, it's a good idea to draw a picture of what's happening. So here, the picture you could probably get away without drawing, but I'm still going to draw it. I've got a circle. I've got some radius. And that radius is increasing. So, right, as it gets bigger, the circle gets bigger. But when you increase the radius by, like, say, an inch, your area increases. Well, it depends on, like, if your radius is already 5 inches and you make it 1 more inch, you're going to get a lot more area increase than if your radius was like 1 inch and you increased it to 2 inches. Right? The further out you are, the more kind of area you're adding on, because your circumference is so much more, even though the thickness is still the same kind of 1 inch of increase. So how do we do this? Well, there's a couple different ways. My thought is usually the following. When I'm doing a related rates problem, I first like to kind of, after I draw my picture, identify what's changing. Specifically, because really there's a lot of things changing here. Like this is a circle, it's getting bigger. One thing that's changing is the radius. Another thing that's changing is the diameter. Another thing that's changing is the circumference and the area. And basically, any facet of this circle is changing. So really, I should say, I want to identify the things that are changing that matter to me. For this first part, I care about the fact that the radius is changing. What's changing? The radius is certainly changing. I care about that. They told me how fast it's changing. And also, they're asking me how fast the area is changing. So in this first part, those are the things that are changing that I actually am concerned about. So the radius, we know its rate of change. The rate of change of the radius is 2 inches per second. And I'm going to write that as dr dt equal to 2 inches per second. You don't really need the units on there, at least not when we get to the equation part, but I like to kind of include them to remind me what's going on. And then the area is also changing. I don't know how it's changing because that's what I'm trying to figure out, but I'm going to say that the area, which I'm going to call capital A, just like I'm calling the radius lowercase r, the rate of change of the area with respect to time is the thing we're trying to find. And I think it's not a bad idea to write in what the units should be. So if the area is increasing, it should be measured in inches squared per second. Because it's an area. So it's some length squared divided by some unit of time to get the rate of change of it. So after we identify what's changing, we then want an equation relating the two or however many variables that are changing. So the next thing we really want is an equation relating the non-time variables. Now, I should say, most of the time when you're talking about related rates, you're asking how something is changing as time goes on. Not always, though. There are some examples where, like, you can do like a pressure, volume, temperature kind of example, like if this chemistry thing, PV equals nRT or whatever. And as your altitude changes, your pressure changes. And so you can ask, like, how is the temperature changing as the height changes? So that's the way where your independent variable doesn't have to be time. But most of the time it is. Most of the time it's just, how is this changing as time goes on and on and on? So I want an equation that relates the area of the circle to the radius of the circle. Typically, this is going to be some sort of well-known geometry formula or some sort of, I don't know, there's usually some sort of geometry thing or Pythagorean theorem or, I don't know, we'll talk about what kind comes up later. So here, the area of the circle equation is area equals pi times the radius squared. And then after that, we're going to differentiate both sides. But we have to be careful here. We're differentiating, pretending like both sides are functions. Well, not pretending, realizing that both sides are functions of time. So with respect to time. Because they are both functions of time, right? As time goes on, the radius changes. In fact, the radius, we could even write an equation for the radius as a function of time if we really want to. We don't really want to, but we could. Same thing for area. The area depends on what time it is. So I'm going to differentiate the area. I'm not just going to get one. I'm going to get the derivative of area being dA dt, the derivative of area with respect to time. On the right-hand side, the constant pi gets to hang out. And what's the derivative of some stuff squared? Oh, it's going to be 2 times our stuff to the first power times the derivative of our stuff, our dr dt. Helpful hint. If the rate you know and the rate you're looking for don't show up in your after you've differentiated both sides, you probably have made an error, right? You want both this thing that we know and this thing that we're trying to solve for. We want both of those to show up after we take the derivative of both sides. finally, I think I can fit this in here. We plug in what we know, solve for what we want to know. So plug in and solve. So I know that the radius is 5 inches because they told me so. And I know that drdt, the rate of change of the radius, is 2 inches per second. And normally what I would write would be that dAdt is equal to 2 times pi times my radius, which is 5 inches, times my drdt, which is 2 inches per second. And normally I would just write 2 pi times 5 times 2. But we could also write the units if we wanted to. We could write it's 2 pi times 5 inches times 2 inches per second to see that the units are going to be what we expected them to be. If we multiply this whole thing out, 2 pi times 5 is 10 pi times another 2 is 20 pi. And the units are inches times inches per second, so inches squared per second. What I should say here is you don't really need to write these units in here. You just need to make sure that the units at the end are the correct sort of units. So if it's how length is changing, it's inches per second or meters per hour or whatever length of measurement, however you're measuring length per unit of time. Or if it's an area, it's like inches squared per unit of time, or meters squared per unit of time, or miles squared, right? Some length squared. And if it's volume, it's some length cubed per unit of time. That's pretty typical. Just to say a little bit more about this example, because this might not seem like super clear as to why this is working out. So let's go back a little bit and say, well, so this is not what we usually do, but this is just kind of to help explain why what we're doing works. We could have said the following. I could have written r as a function of time. I could have said, yeah, the radius is increasing at 2 inches per second. So I could say that r as a function of time is 2 times t inches, where t is measured in seconds. So then after 1 second, my radius is 2 inches. After 2 seconds, my radius is 4 inches. After 3 seconds, my radius is 6 inches, and so on and so on and so on. Every second, the radius increases by 2 inches. So it's very, very fair to say that r prime of t, or dr dt, is equal to 2 inches per second. Also kind of worth seeing, just because I think it's nice to know, when you have something that's measuring something and you take its derivative with respect to time, you pretty much, your units get divided by that unit of time. So if your function is measured in inches and you take its derivative, you're asking how it's changing. Its rate of change is measured in inches per second or per whatever unit of time we're talking about. And then let's talk about the area function. So the area function is pi times r squared, or written in terms of t, our area as a function of time is pi times r as a function of time squared, which we could actually plug in our r function and say, cool, our area as a function of time is going to be pi times 2t 1d squared. And again, I really should stress, this is work that you normally wouldn't do. I'm showing it because I think it's helpful to see what's going on, but we would usually not do this at all. So, in fact, we can even go 2 different ways here. So we'll look at both of these. We'll look at this, and we'll look at this, because this one is actually not super helpful here. So let's look at the top one first. So I look at a of t equal to pi times r of t squared. It's a little easier to see that when we take the derivative of both sides, we get what we get. If I differentiate here, the derivative of a function is its derivative. It's a prime of t, or if you prefer, dA dt. And on the right-hand side, again, the pi hangs out. The derivative of something squared is 2 times our something to the first times the derivative of our something. But look, that's essentially exactly what we wrote right there. dA dt equals pi times 2 times r times dr dt, just using different notation. And then we can plug in what we know. So here's the thing we don't know. In this problem, I told you what r is equal to. I didn't tell you what time was equal to. We could go back and figure it out. If the radius is 5 inches, I guess the time had to be 5/2 or 2.5 seconds. Because you plug in 2.5 for t, or 5/2 for t, 2 times 5/2 is just 5. So finding our derivative at that time, we're going to get pi times 2 times our radius at time 5/2 times our derivative at time 5/2. Which again, that's kind of weird to write, but it's fine. So let's see if this works out the same. If I plug in 5/2 for my time, my radius is going to be 2 times 5/2, which is 5, which shouldn't surprise us because we were told to figure out what's going on when the radius is 5 inches. We almost are doing too much work here. And then the derivative is 2. And if I plug in 5/2, there's nowhere to plug it in. The derivative is still 2. The derivative is always 2 because it's a constant rate of change. And look, we get the exact same answer. 2 pi times 5 times 2, which is 20 pi inches squared per second. And I actually don't think it's really useful to kind of go this far. And you could, right? You could totally write the area is 2t times 2t is 4 times pi times t squared. You could say the area is that and then take the derivative. But here I just feel like it's kind of divorced of all the meaning, right? You can take the derivative and get 8 pi times t, and you can plug in 2.5 for t, or 5/2 if you prefer, and then you're still going to get 20 pi. But the point isn't to do it this way. The point is to kind of observe things at the higher level where we're not having to delve down into the nitty-gritty of what time is it when things are happening. We're just kind of using the information that's given and trying to figure out what's being asked for without doing more than we have to. So again, I'll say the usual 4 or 5 steps for this process, and we'll write them down again, but we're going to first draw a picture if it helps. Usually it helps. Figure out what's changing, what we want to know is changing. Find an equation relating those things, differentiate both sides, plug in, and solve. So, with that in mind, let's look at another example. Yeah. Let's keep your papers in order. Sure. Gabriella. Actually, what's up here, right? Looking at that. That's better. That's smart. Gabriella is standing 6 feet away from her sister Mia, who is holding a balloon. Sadly, she lets go of it. She lets go. And the balloon rises at a constant rate of 4 feet per second. After 2 seconds have elapsed, how fast is the distance between Gabriella and the balloon changing? So we're definitely going to draw a picture. And I would say a key thing to think about when you're drawing a picture is that things that are changing should get variable labels, and things that are not changing should get labeled by whatever value they happen to be equal to. So here's what I'm thinking. Gabriella standing over here, Mia standing over here. They're 6 feet away from each other, and that distance is not changing. But then Mia lets go of the balloon and starts going up, 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 up. And this distance from Mia to the balloon is changing. So we're going to give it a variable name. Wow, that was interesting. Typically for a vertical distance, I like either y or h. H for height, Y because that's usually our distance. So I'm gonna use Y here. And then we're curious or interested in how fast the distance between Gabriella and the balloon is changing. And for that distance, I usually use the letter S or Z. Typically for diagonal distances, S or Z is pretty typical. Yeah. All right, so there's our picture. Now let's ask, or let's just say, let's answer the question, what's changing? And again, really the parenthetical there is what is changing that we care about. Well, we've labeled those things. So in this case, we know that Y is changing. And the rate of change of Y, oh yeah, thank you. Yes, I should pass that out. The rate of change of Y is dy dt equal to, well, they told us that the balloon was rising at a constant rate of 4 feet per second. And we also know that Z is changing, the distance between me and the balloon. The rate of change of Z is equal to, well, that's what we're trying to find. So we've identified the thing that we know is changing, the thing that we want to find how it's changing. So now we need an equation relate. Oh, question? Okay, now we need an equation relating those two variables. And this is where the geometry comes into play. So here I see a right triangle. And when I see a right triangle, it's almost always going to be either some sort of similar triangle thing or some sort of Pythagorean theorem thing. And when I say sort of, I mean Pythagorean theorem. And it is Pythagorean theorem. We can definitely relate Z and Y by saying that this squared plus that squared equals that squared. So my equation is going to be, I should say the equation relating the non-time variables or the not independent variable, the dependent variable. So if it's not time, something else, same deal. So here we're going to say 6 squared plus Y squared equals Z squared is our equation. And then we're going to differentiate both sides. Okay. What's the derivative of 6 squared? What's that again? Yes, 0, right? Because 6 squared is just 36. It's a constant. Even though sometimes people will try to trick you. They'll say, what's the derivative of e to the 7th? And you're like, no, it's not e to the 7th. It's 0. It's a constant. There's no x. There's no variable. Derivative is 0. So the derivative of 6 squared is 0. The derivative of y squared is 2y times y prime, which I really meant to write dy dt there. That feels terrible. Let's try that again. 2y times the derivative of y, which is dy dt, equal to the derivative of z squared is 2 times z times dz dt. We're almost always using essentially implicit differentiation here, or if you prefer the chain rule, it's the same thing, right? I'm taking the derivative of both sides. I'm pretending that well, I'm not pretending, everything is a function of time. So when I have y squared, I can really think of this as y of t squared, and that is really z of t squared. And when I differentiate it, I get 2 times y of t to the first times the derivative of my stuff. When I differentiate that, I get 2 times z of t to the first times the derivative of z. Almost every time when you're doing related rates, if you're differentiating some variable, it almost always gets multiplied by the derivative of it with respect to time, because it's always a chain rule thing that's happening. And now we plug in what we know, solve for what we don't. Yeesh. Can I write numbers maybe? That looks terrible. Also, yeah, okay, fine. So plug in and solve. I will point out, if you wanted to, you could divide both sides by 2 and it would make it less complicated, but we don't have to do that. We can say that we have 2 times y. What is y? They didn't tell us. They said the balloon was rising at 4 feet per second, and then they said 2 seconds after you let go, what's going on? Well, if we're rising 4 feet every second, and it's been 2 seconds, how many feet have we risen? 8 whole feet, 4 times 2. So our y value is going to equal 8 feet at the moment of interest. We got 2 times 8 times dy dt, which they told us was 4 feet per second. Notice how I'm not writing my units in this time because I don't really want to. I'm just going to write them at the end. Equal to 2 times my z value, which they also didn't tell me. But we can find z by using the Pythagorean theorem. So we can say, oh, look, if I want to find z, well, I know that 6 squared plus 8 squared is going to equal my z squared. Most of the time when people give you these kind of problems with the Pythagorean theorem in them, most of the time the numbers work out nicely. Meaning usually your triangle is a multiple of a 3, 4, 5 triangle or a 5, 12, 13 triangle. Those are called Pythagorean triples, where the numbers are like nice, perfect integer numbers, and 5 squared plus 12 squared does equal 13 squared, and 3 squared plus 4 squared does equal 5 squared. And here, this is exactly twice a 3, 4, 5 triangle. 3 times 2 is 6, 4 times 2 is 8, and 5 times 2 is 10. Or you could do the math. 36 plus 64 is 100. If that equals z squared, then oh yeah, z is the square root of 100, which is going to be 10. For these problems, you should always be able to fill in everything except for the one thing you're trying to actually find. Everything else should be either given to you or findable based on the information we have. And now we're going to divide both sides by 20 to solve for dz dt. So we're going to get that 2 times 8 times 4, which is what? I should just leave it as 2 times 8 times 4. 2 times 8 times 4 divided by 2 times 10 is equal to dz dt. So writing out my final answer, dz dt is going to equal, let's see, cancel the 2's. 32 divided by 10 is 3.2. And now I should write the units in at the very end. So since z is a measure of length, my dz dt should be that unit of length divided by the unit of time. So in this case, it's going to be 3.2 feet per second. And for related rates problems, it's a good idea to write in the units at the end. Or whenever you want. But definitely your answer should contain the correct units when you're solving problems like this. Let's see, what else have I got? Okay, we got a few more things here. Oh yeah, that's a good one. We'll try to do enough of these so that they seem not too terrible, but there's other things to talk about too. So we'll do 2, maybe 3 more. Probably 2. Okay. So let's look at this next one. I feel like I'm just slightly in the wrong part. There, that's a little bit. So here we go. So the setup here is that the radius. What's going on? I feel like I keep like doing something funky here. Sorry about that. The radius of a cylinder is increasing at 3 feet per hour, while the height is decreasing at 2 feet per hour. How fast is the volume changing when the radius is 5 feet and the height is 10 feet? Question, yeah. I would, yes. If you're near the end of the page, definitely. These problems almost always take up a whole page for me. All right, so usual steps. I'm going to draw a picture. My shape is a cylinder. I'm going to draw a cylinder. And since they've told me that both the height and the radius are changing, I'm just going to label that as the height, and that as the radius. So whatever is changing. So I will point out, they also have asked about the volume. The volume is changing, but there's not really a way to label the volume of this thing, right? You can put a V like in the middle of it, but that seems weird. So we're not going to label the volume or the kind of the bigger dimensional thing, just the things that are easy or reasonable to label. So as usual, what's changing? Well, the radius, the height, and the volume. So we know that the rate of change of the radius, they told us, was 3 feet per hour. The rate of change of the height, well, it's not 2 feet per hour, it's negative 2 feet per hour because the height is decreasing at a rate of 2 feet per hour. So if you have something that is getting smaller, its rate of change or its derivative should be negative. Or if something's decreasing, its derivative is negative. Something's increasing, its derivative is positive. So dHdt is going to be negative 2 feet per hour. And finally, we're trying to find dV dt. We want an equation relating all the things we know and are trying to find. So in this case, we need the equation for the volume of a cylinder. The volume of a cylinder is the base area, which is the area of a circle. So it's pi r squared multiplied by the height. No, that's not worth saying. So then step 3, we're going to take the derivative of both sides. Or, yeah. So almost always, no, not always. The last example we didn't. A lot of the time, like one side is just the volume or the surface area or whatever, and you just differentiate it and you get dV dt or the derivative of that thing. But in the previous equation, we did use implicit because we had like y squared equal to z squared plus 6 squared plus y. So like, you differentiate both sides. Some of the times it's just like, yeah, the derivative of that's dV dt. On the right-hand side, though, we are going to have to use the product rule. So we're going to leave the pi constant out in front. The derivative of r squared is 2 times r times dr dt. And then we leave h alone. Plus, then we switch it up. We leave r squared alone, multiplied by the derivative of h, which is dh dt. Now we plug in what we know, solve for what we don't. So I'm trying to find dV dt, so it's nice it's already by itself. So dV dt is going to equal pi times 2 times the radius, which they told me was 5 feet, times dr dt, which they told me was 3 feet per hour, times h, which they told me was negative 2 feet per hour. No, sorry, h, not dH dt. They told me h was 10 feet. Sorry about that. That's 10 feet. Plus r squared. Again, r is 5 feet, so that's 5 feet squared times dH dt, which is a negative 2 feet per hour. I did write the units here because I wanted to point out we do get the right units. If we multiply feet times feet per hour times feet, we get feet cubed per hour. How our volume is changing. Same deal here. Feet squared times feet is feet cubed per hour. So they're both in cubic feet per hour. So simplifying this, we get pi times, let's see, 2 times 5 times 3 times 10 is 10 times 10 times 3, which is 300. And then 25 times negative 2 is 50. That's minus 50. So we end up getting 250 pi cubic feet per hour. Interesting. Kind of. Yes. This part here, so that's the 10 feet. So this h here is supposed to be 10 feet because that's the value we were given for h. But I started writing the wrong thing and tried to fix it, but clearly did a bad job of it. Sometimes that happens. Okay. Let's look at, one more, and then we'll move on. So I will point out, in my opinion, this kind of example is a little bit less likely something you will see because most of the time when we give you problems, I feel like this isn't super true, but a lot of the time our function is usually a function of one variable, not a function of two variables. And what I'm really referring to is what we're going to see in this next example. So one more example of this, and then we'll move on to whatever the next thing is. Sorry, I should make this up here so you can see it. So here's our next example. A water tank in the shape of an inverted cone, meaning pointy side down, with a radius of 4 meters and a height of 12 meters is being filled with water at a rate of 5 cubic meters per minute. When the water in the tank is 6 meters deep, how fast is the water level rising? So half the battle with problems like this is reading all that and then kind of distilling down what's actually important to write down or kind of transfer to a graph. So I've got a cone, point down, looks like that. That's my tank. The cone itself isn't changing in size, right? The cone has a radius of 4 meters and a height of 12 meters. What is changing is the depth of the water or how much water is in the tank. So you've got some water in the tank and that water level is rising as we keep filling it. So for this smaller cone of water, its height and its radius are changing as we add more water into the tank. So we're really interested in that radius and that height, which are both changing. So the things that are changing that we care about, the radius, the height, and the volume. Well, one of those is a lie. Because in the problem, they only told us how, did I even tell you? No, yeah, they only told us how the volume was changing, right? We're filling this thing at a rate of 5 cubic meters per minute. So they're asked, or we've been, oh my gosh, can the words come out? The volume rate of change is 5 cubic meters per minute. Because we're adding water in, right? There's going to be more water, so the rate of change of the volume of the water is positive. And then we're being asked about how fast the water level is rising. So we want to know what dH dt is equal to. We actually don't know or really care how the radius of the top part of the water there is increasing. It is, but we don't really need to know it. And you'll see why in just a minute here. So the second part here is getting an equation involving, we would prefer involving only the volume and the height. But at the get-go, that's not an option. So the equation for the volume of a cone is 1/3 the volume of a cylinder with the same dimensions, which is kind of cool. I remember in my chemistry class when I was in high school, like my chemistry teacher had like a cone that was like plastic you could fill with water, and the cylinder was plastic you could fill with water, and the cylinder and the cone have the same radius and the same height, and you fill up the cone 3 times and put it into the cylinder, and it was exactly the same amount of volume. So a cone really does have 1/3 the volume of a cylinder with the same radius and height. Or you can remember it's 1/3 pi r squared, but that's less fun. The problem here is h is in that equation, and I don't know how h is changing, and I don't really want to. here's where something extra comes in. So for cones especially, there's usually an extra step here where we have to eliminate one of those variables by finding a relationship between the radius and the height of the cone. Now, here's what's nice about this cone. We already know what proportion the radius is to the height. The radius is 4 meters, the height's 12 meters. So I would say the radius is 1/3 of the height. And that's accurate. There's actually, it really feels almost like too straightforward sometimes. You could do more work here. If you really wanted to, you could say, draw this right-hand side of the cone as some similar triangles, where this larger height is 12, this radius is 4, and then my water, the radius is r, and that height is h. And then I could set up a proportion using similar triangles. And I could say you can do it kind of almost any which way you want. The smaller height divided by the larger height is equal to the smaller radius divided by the larger radius. And then I could, since I'm trying to eliminate r in my equation, I'm going to solve for r. So I'm going to say multiply both sides by 4 and get 4 times h over 12 equals the radius. And if I reduce that fraction, I get h over 3, or 1/3 times h is equal to the radius. So like I said, the radius is 1/3 the height. Because in the larger cone, the radius is 1/3 the height. And the proportion never changes. If you're filling this cone up with water, every smaller cone as you fill it up still has the same proportion of radius to height. In a different cone, it'd be a different proportion, but it would still be a constant throughout filling it up. So if you're doing a problem like this and you have to do that, you can really kind of just look and say, okay, the radius to the height is 4 to 12 or 1 to 3. So the radius is 1/3 of the height or 4/12 of the height. So then we can go back and say our new equation is going to be the volume equal to 1/3 times pi times replace the radius with 1/3 the height squared and times the height again. And then simplify that. So we're going to get the volume on a new piece of paper is equal to 1/3 pi times 1/3 squared is 1/9 h squared times h. Simplifying that, we're going to get to the volume is equal to pi over 27 times h cubed. And now that's much easier to take the derivative of both sides. So now, good old step 3, or typical step 3, differentiate both sides. You're going to get dv dt equal to the constant pi over 27 hangs out. The derivative of h cubed is 3 times h squared times the derivative of h. Now we're going to plug in what we know, solve for what we don't. So we know that dv dt is equal to 5. I'm also going to simplify as I go here. Pi over 27 times 3 reduces to just pi over 9. And I'm going to plug in my h, which was 6, I believe. And then dh dt is the thing I'm trying to solve for. So let's simplify. We're going to get 5 equal to pi over 9 times 36 times dh dt. And although I could solve for dht right away, I think it's better to simplify this first and say 36 over 9 is just 4. So I really have 5 equal to 4 pi times dh dt. And then solving for dh dt, we get dh dt equal to 5 divided by 4 pi. And it's going to be measured in meters per minute. Because my volume was changing and the units were meters cubed per minute. So it's a height. So related rates problems, it's always going to be a word problem. There's going to be lots of words. But okay, what's changing? What do I want to know is changing? How do I relate them? Differentiate both sides, plug in what you know, solve for what you don't. Okay. Where to go to now? Yeah, I think it's sure. Sorry, I got things all over the place here. One second. Let me get back in. Yeah. All right. So the next part is actually super duper important for anyone taking 17B and or 17C. Especially in 17C, the idea we're about to introduce comes back kind of full, like you spend a good 3 weeks talking about the stuff that we're going to cover right now, but just in a very different but yet the same way. I know it makes super sense, not at all, but it will eventually. So here's the idea. Yeah. We want to solve the differential equation. You're going to be doing a lot of in 17b. dy dt is equal to k times y. We're actually not going to solve it. We're going to say what the solution is. Later on in 17b, you'll actually solve it. So what does this say, though? Because really, what's more important here is understanding the meaning of this differential equation. So a typical way to imagine this is to imagine that y, or y as a function of time, is our population size. And it can be the population of people, bacteria, or the amount of radioactive material, or kind of anything you measure that either grows or decreases. And then dy dt, well, it's the derivative. It's the rate of change, or the rate of growth of the population. For radioactive substances, dy dt is usually the rate of decay. And it's usually a negative number because you have less radioactive material as time goes on. But it's just the rate of change of your stuff. And so what this equation says that the rate of change of y is a multiple of, or is proportional to, y itself. What we're saying here is the rate of growth of the population is proportional to the population size. If you have more people, the rate of growth is going to be larger because more people are going to make more people. The more people you have, the more people you're going to make. Now, if I said the population was growing at 1,000 people per year, it's not super meaningful. Are we in Davis? Sure, it's meaningful in Davis, right? If I say Davis is growing at 1,000 people per year, that's a big increase for a population of what, 60,000-ish. If we're in New York, not very meaningful, right? If New York is growing at 1,000 people per year, they're probably having some serious problems because it's not the usual population growth. So really a more useful kind of piece of information is the relative rate of growth. So I just want to point out, even though, again, this is not super where we're going, I'm just going to point out that the relative growth rate, when you take the rate of growth divided by the population size, you can also think of it as the per capita growth rate. Per capita growth rate. For this sort of situation, if you just divide both sides by y, the rate of growth divided by y is constant. And we're about to say what the solution is. In fact, some of you probably already know. So what I'm really trying to point out is all these words mean the same thing. So if someone tells you the rate of growth is proportional to the population size, or if they tell you the relative growth rate is constant, or if they tell you the population grows exponentially, those words all mean the same thing. We're just saying it in a different way. And the reason I point that is because people will say it in these different ways and kind of expect you to know that, oh yeah, we mean the same thing here. So how does this kind of end up being exponential growth? Well, check it out. If you were to say that the function for your population was, say, like something like y of t equal to c times e to the kt, where c is a constant and k is a constant. K is the same k as over here. If we took the derivative of both sides, dy dt, the constant hangs out. the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Okay, k is a constant, but t is the variable. The derivative of k times t is k times 1. But check it out. That's just my population function multiplied by k. Where's my red pen? Right? That's just your y of t. So this is literally equal to k times y. So the rate of change is proportional to the population size, or the rate of growth is a multiple of the population size. So that just means we have exponential growth, or again, decay if the population is declining. This idea that the derivative of something is equal to a multiple of that something, that is the specific idea that's going to come back like in the 4th week of 17C, when you're talking about solving linear systems of differential equations. And you're going to have this derivative equal to something times the original function, and it's going to come back to this idea. So I know it's a ways away. Definitely, when you get there, you'll be reminded of it by us, but just keep that in mind for 17C. Like, oh yeah, we're talking about exponential growth and decay because we have this sort of relationship. Okay, what do we actually want to do with this for now? Good question. So usually what we do is we try to kind of set up some situation and solve for some things. So yeah, let's look at an example. Oh yeah, this is where we kind of go a couple different ways here. So let's say we have the following. A bacterial culture initially contains 200 cells and grows at a rate proportional to its size. Okay, those are the magic code words that say we have exponential growth, right? Grows at a rate proportional to its size means we have exponential growth. After 3 hours, the population has increased to 700 cells. Question A, find the population size after T hours. This is a terrible way of saying write the population as a function of time. That's what this question actually means. Write the population as a function of time. Okay, so here's what we know. We know a couple things. We know one, we know that our model for the population size at time t is going to be y of t equals some c e to the kt. And unfortunately, because I feel like we kind of talked about this earlier in the quarter a little bit with like things growing, doubling every so often, right? That was something we talked about, I think. It's hard to remember what I talked about this class. There was kind of a slicker way of doing this where you just kind of made it work without kind of doing all of the intermediate steps. It's less of an option here because we have less nice numbers, right? We're not doubling every 3 hours. We are multiplying by some terrible amount every 3 hours. You could actually still do it that way if you really wanted to, but we usually don't. So here's the setup. I still like to draw my little table with times on the left and amounts on the right. And at the initial time, at time 0, this has 200 cells. And 3 hours later, I have 700 cells. Now be careful. I was just thinking about this. If I just changed one word, I could change this 700 to 900. If I had said the population has increased by 700 cells, then that would be a 900 after 3 hours, not a 700. So you have to read the words. Usually people don't do it that way, but I could see someone doing it that way just to make it a little extra tricky. So you have to read the words carefully. All right. So it's always nice when you have time equal to 0, because that usually just means that the amount of stuff ends up being the constant c. We can still do the work, or if we take this initial time and population and plug it into our model, we're going to get 200 equal to C times E to the K times 0. K times 0 is 0, E to the 0 is 1, C times 1 is C. So we do get C equal to 200. Great. We write our new updated model as y of t equal to 200 e to the kt. And then we plug in our other data point. So now population is 700 equal to 200 e to the k times 3. Solving for k does require more work typically. So we always divide both sides by whatever's multiplying by e to the stuff. So that's going to become 700 over 200, or I'll just write 700 over 200 equal to e to the, I do prefer to write this as 3k to the k times 3, but it doesn't really matter. Then we take the natural log of both sides. I am going to change that to 7 halves instead of 700 over 200, right? It's easy to reduce that fraction. So we're going to have the natural log of 7 over 2 equal to the natural log of e to the 3k, which is just 3k. That's why we're taking the natural log of both sides. So then, from natural log of 7 halves equal to 3k, we're just going to divide both sides by 3. Or multiply both sides by 1/3 is probably how I'd actually write it. You can say that 1/3 times the natural log of 7 halves is equal to k. And now we can write our updated model again as y of t. It's kind of horrible to write, but we're going to write it anyway. It's 200 e to the 1/3 natural log of 7 halves times t. That's your entire exponent there. Sorry, that's a little close for comfort there. Some people, and I think we've seen this, I think we saw this earlier in the quarter, some people would prefer to write this as 200 exp of 1/3 natural log of 7 halves times t. When you see exp, that just means e to the power of whatever's in the brackets. Yeah.
Why did you double the exponent? Like, why did you put the exponent to, or wait, or is that just, sorry, I didn't realize that was a line.
No, it's okay. Oh, like you mean like right here?
Yeah, I thought that was.
Yeah, that's why I do the line there to kind of like, that's a little close for comfort. Yeah, no problem. Other questions? Yes. Because I like writing times 1/3 better. I like to avoid fractions in fractions if I can help it. And I felt like natural log of 7 over 2, all divided by 3, just looked like it would take up more vertical space. But not for any good reason. You could totally write it as natural log of 7 halves divided by 3 times 2 if you wanted to. I will point out, just because I think it's kind of interesting to know, you could totally do this the other way. You could say that, great, in a 3-hour period, we multiply by 7 over 2. That's what's always true about exponential growth or decay. For every set amount of time, you always multiply by the same amount. So if we went to, say, another 3 hours, we would end up multiplying by another 7 over 2. It's kind of interesting. So you could definitely also write this as y of t equal to 200 times, instead of writing it as e to the 1/3 natural log of 7 halves times t, you could write it as 7 halves to the t over 3. So that when t is 0, you get 200 times 7 halves to the 0, which is 200. When t is 3, you get 200 times 7 halves to the first. 200 times 7 halves is 700. So every time t increases by 3, this power increases by 1, and we multiply by another 7 halves. So that's another way of saying we have exponential growth, is that the amount you multiply by every, in this case, 3 hours is constant. It's kind of an interesting fact. It's better said like the doubling time is constant, or the half-life of your radioactive material is constant, because it's the amount of time it takes to double, or the amount of time it takes to cut in half. Same idea. The amount of time it takes to multiply by whatever your multiplication factor is a constant when we're talking exponential growth or decay. So now that we have found the model, we could ask a question like, what is my question here? So we've done the exciting part. The rest is not as exciting, but the questions you can typically ask are either how much bacteria do you have after so many hours have passed, or how long does it take until we get so much bacteria? Those are really the only things you can ask. Sometimes you can ask weirder stuff, but that's about it. So, for example, we could ask how many bacteria after, I don't know, 5 hours. I should be clear here. It's almost always from the beginning. So after 5 hours from when the population was 200. So that's the easier version. That's just you're plugging in t equals 5 and that's your answer. So if my model for growth, or for the, I should say, my model for the amount of stuff at time t is 200 e to the 1/3 natural log of 7 halves times t, then my answer here is going to be y of 5. I'm just going to plug in 5 for t, and there's not really anything else I can do without a calculator. I'm just going to leave it as 1/3 natural log of 7 halves times 5. I suppose I might simplify this, although it's not really simplifying it, as e to the 5/3 times natural log of 7 halves. But that's all I can really do without a calculator. And that's all you should do on an exam. If someone asks you this question, how many bacteria there are after 5 hours, that's your answer, and you're sticking with it. And then the other question, which is a little more interesting, is how long until there are 2,000 bacteria? And so again, well, I should say alternatively, instead of plugging in time equal to 5 hours, we're going to substitute in y equal to 2,000 bacteria. So our equation is going to be 2,000 equal to 200 times e to the 1/3 natural log of 7 halves times t. And much like solving for k, we're going to do the same 2 or 3 steps. We're going to divide by 200 equal to e to the 1/3 natural log of 7 halves times t. We're going to take the natural log of both sides. By the way, 2,000 divided by 200 is 10. So we're going to have the natural log of 10 equal to, okay, the natural log of e to the stuff is just the stuff. So the natural log of e to the 1/3 natural log of 7 halves t is just going to be 1/3 natural log of 7 halves times t. And now we're going to solve for t by multiplying both sides by 3 and dividing both sides by natural log of 7 halves. And again, the answer is not particularly lovely, but it is an answer. So that's how long it takes to get to 2,000 bacteria. And it's 1:31, so I should stop. There is another interesting question to ask here, but I guess we'll have to wait until the first half. All right, I have office hours over in CADS, and I'll see you all on Thursday. Make sure you got your name on the sign-in sheet if you didn't already. And have a lovely day. Where'd you? You're welcome. Oh, there. Page. Yes. This one? Oh, it's right there.